Welcome back. So our goal for today is to think about how we can take our discussion of Coulomb's law, which then extended to a vector expression for Coulomb's law, which helped us to talk about the electric forces on a given charge with respect to another charge. And I hope to generalize that past just point charges and start to talk about what could happen to a charge in the presence of another charge distribution. So, this is the vector expression for Coulomb's law that we wrote down last time. F12, and remember we read that as the force on charge 1 due to charge 2 is equal to k q1 q2 over r12 squared, where r12 is the magnitude of that vector r12, and let me just, I'll even write down r12 was equal to r1 minus r2, right? That's that vector that points from 2 to 1. And then times r12 hat, where r12 hat is just the vector r12 divided by the magnitude of the vector r12. Now, this is a great expression when I'm talking about two charges, and I'm looking at the force on charge 1 due to charge 2. But what happens if there are more forces influencing charge 1? Well, I can easily take this expression and now generalize it to a sum. So now I want to talk about the force on 1, that is the total force. Well, that is going to be the sum over all of the other charges involved of, well, what is the vectors that correspond to each one of the forces? Well, it's given by the above expression, k, q1. Now, each of the individual charges plays the role of q2, so I'm going to call that qi. And then I'm going to divide it by r1i squared times r1i hat. And my notation here is getting a little bit complicated to follow in the sense that now I have a sum and I have an I, but I don't want to lose sight of the fact that it's a really beautiful expression, right? That I can now identify all of the other charges, which I'm calling the q sub i's, and I can now say, if I know where all those q sub i's are, and I know what all of the charges q sub I are, I can reconstruct the entire force on q1. Now, the really beautiful thing about this expression is that I can quickly see that I'm going to be allowed to convert this expression to something where my individual charges qi are no longer just point charges, right? This was the whole point of calculus, that if I can take some distribution or some continuous description of, in this case, charge, and I can break it up into tiny little segments, then I can integrate over those segments, and the integral over those segments is akin to a Riemann sum, right? And so whenever I see a sum, I say to myself, well, if I make those q sub I small enough, that is, if I let q sub I go to dq, that is, if I let every individual charge go to some infinitesimal charge, then that sum over I is going to go to an integral. And I'm going to be allowed then to do integrals over all of the different charges. And that's why this is so powerful, because if I have some test charge, in this case we're still calling it q1, but I have some test charge q1, and I want to talk about what is the force on that test charge due to whatever charge distribution I have, I can now use this expression to build an integral that's going to help me to understand what that charge is, what that force is on q1. Now, just for notation's sake, once I start talking about one charge that I'm interested in, and I'm talking about a charge distribution that I'm looking at, it becomes a little awkward to call that charge 1. And so I'm going to just relabel that charge to charge 0, right? If I call it charge 0, then it's like my test charge, but it's something that doesn't even have a number, right? It's a really special thing. It's charge 0. So I can say that F0, the force on charge 0, is going to be equal to k. And I'm going to convert my sum into an integral. So the integral And now I have my Q0. That's always going to be present because the interaction between my test charge and any of the infinitesimal charges is still going to rely on the magnitude of my test charge, times dq. Well, now what's going to happen to R12? Well, R12 is now going to have to represent the vector that points from my little segment dq to the charge that I'm interested in. And so if I promote, let me go over to the example that I'm familiar with, right? So over here, I had Q1, and I had some Qi, and I calculated a bunch of R1i's, right? Those were those vectors. Over here, I have a Q0, and I have some charge distribution now that's broken up into infinitesimal segments, which we're calling dq. Well, now I need a vector that represents the infinitesimal, or the infinitesimally defined vector that goes from dq to q0. And now, for better or worse, what we call this is r. Okay? Now, you have to bear with us because there are only so many different ways to write r. But whenever I'm talking about r inside my integral, when I'm talking about electric forces, this r is going to be the vector that points from my charge distribution, so from any point on my charge distribution, any infinitesimal segment of charge, to the place where I'm looking. And so now, in here, I have the magnitude of r squared in the denominator times r hat, where of course r hat is just r vector divided by the magnitude of the r vector. And this thing here is going to be of great use to me, because as long as I can take my charge distribution and I can break it up into little pieces dq, and then I can mathematically represent how far is that little piece dq from the test charge that I'm interested in studying, then I can just evaluate this integral and I can go a really long way. Before I do an example, I do want to just say that this integral, f0 is equal to k times the integral q0 dq over r squared r hat. When I'm talking about this integral in this form, it's actually kind of hard to do. It's hard to do calculations with it because I don't really know what it means to define a little dq. And so in general, when I'm actually doing a calculation, I have to ask myself, what does my charge distribution look like? And so generally, my charge distribution comes in three different flavors. If it's a line, then I say dq is equal to some charge density, which we generally call lambda, times dx. That is, I take a little segment dx of my line, and I multiply it by how much charge density is on that line, and that gives me how much infinitesimal charge do I have. It could also be equal to sigma dA, that is, how much charge density is there on a surface, multiplied by the infinitesimal area of that surface, or it could be rho times dV if I have a three-dimensional volume. And so it all depends on how does the problem stack up. If my charge distribution is a line, then I'm going to replace dq with lambda dx. If my charge distribution is a surface, I'm going to replace it with sigma dA. And if it's a volume, then I'm going to replace it with rho dV. Okay, well, it seems to be the ideal time now to do a quick example. So let me consider this one-dimensional charge distribution, which is just going to be a rod. And I'm going to lay that rod along the z-axis. I'm going to say that rod has length L. And then the charge that I'm going to be studying is to the right of it. It's along the x-axis. And I'm just going to call that charge Q. And so I know, if I go back to my expression for the electric force, that the force on Q is going to be given by K times the integral of Q times dq, where this dq is my charge distribution, divided by r squared r hat. Now, it's a one-dimensional charge distribution, and so dq is going to be equal to my charge density, lambda, right? And I'm using the same symbol as I used on the previous page, right? Lambda is going to be the charge per unit length. And then I'm going to say, well, it's that much charge per unit length, of course, in some direction. And since I've set up my rod in the z direction, I'm going to multiply lambda by dz. Okay, now I already feel more comfortable because as I do this integral, I'm going to have to do the integral over the charge distribution, and the charge distribution is laid out in the z direction. This is something that mathematically we call a parameterization of the charge distribution. That's a word that we're going to get. That's a word that we're going to talk about in the future. But of course, this charge distribution isn't there for all values of z, right? It's really only there for z in some interval, which is going to be between minus L over 2 and L over 2. Okay? And so that's just something to keep in the back of your mind, that when we talk about this charge distribution, it's something that isn't defined everywhere. It's only defined from minus L over 2 to L over 2. Now I have to define my vector r, which is going to, remember, point from my charge distribution to my charge. Now, how I like to set this up is I take some infinitesimal piece of my charge. So I'm going to call this dz, right? It's a little bit in the z direction. And I want to say, well, how far, or rather, what is the vector that describes the distance between dz and the charge that I'm looking at? And now, again, like we saw in the last video, things really start to come together when I do these simple examples, right? Because this vector r now is something that I can define by looking at it at the in the diagram, right? I know that the vector r points downward and to the right. It's going to have an x component that corresponds to how far away is q on the x-axis, and a y component that corresponds to my vertical distance. So if I say that the x distance here is just x, and the y distance in the vertical distance is given by z, well, I've almost completely identified my vector r, with the exception that, well, if z is positive, in what direction is this vector pointing? It's pointing down and to the right, which means that the vector r actually has a minus sign here. This takes a little bit of art, or a little bit of getting used to. But my vector r always points from my charge distribution, whatever point I'm looking at, to the test charge, and therefore r in this case is going to have an x component that's equal to x, and a second component that's equal to minus z. It's going down and to the right. Therefore, r hat is going to be equal to x comma minus z divided by the magnitude of r, which is the square root of x squared plus z squared. Okay. Now, all I'm doing here is I'm plugging into the definition, and it seems like it feels like I'm doing things. It feels like I'm doing things too easily, but really, sometimes calculus actually makes our lives easier, right? If I define this r hat in this way, well, this is just what r hat is, right? And of course, when I did that, I used the intermediate step that the magnitude of the vector r is equal to the square root of x squared plus z squared. And it's not a good idea to skip that step because, of course, I need the magnitude of the vector r in order to write down the integral. And so now I can take my expression and I can plug in what I know. So f on q is equal to k times the integral of q. And now I have my dq, which is lambda dz, times r hat over r squared. Well, that's going to be x comma minus z. And that's, in the denominator, I have a square root of x squared plus z squared from my r hat. I also have a square root of x squared plus z squared from my r squared. And so in the denominator, I really have an x squared plus z squared to the 3 halves. Now, I'm almost done. In fact, I'm mostly done with all of the physics because I've now written down an expression that I can totally evaluate, right? This thing is now just a couple of integrals. But before I do that, I want to make sure that we understand what I just said. It's a couple of integrals, right? The thing on the right-hand side is a vector. That is, it has two different components. The thing on the x comma minus c is a proper vector. And therefore, this thing is really two different integrals. And this might be our first time seeing something like this. But everything that I have outside of my vector can be, we can use the distributive property, right? And move all of the integrals and all of the algebra inside the vector so that I can really talk about the x component of this vector and the y component of this vector. So the x component is really k, and I'm going to pull out the q just because it's a constant in this integral, and the lambda is as well. So kq lambda times the integral of x dz over x squared plus z squared to the 3/2, comma, kq lambda times the integral of minus z dz over x squared plus z squared to the 3/2. Okay. And at this point, the physics is really done, right? I've come up with an expression now in terms of two integrals, and I guess before I should end, it's important for me to note that these integrals are not over all possible values of z, right? They really go from minus L over 2 to L over 2 because my charge distribution is only defined from minus L over 2 to L over 2, and therefore I have definite integrals to evaluate. They're not easy definite integrals, but they're just definite integrals that I can evaluate. And I'm going to leave that, I'm going to leave those definite integrals for you to verify on your own. The way that I did them was I went to a table of integrals to make sure that I could look up the antiderivatives for these two different expressions. But at the end of the day, what I get when I do this evaluation is I get that the second integral vanishes, and that's because there's a symmetry in this integral over z. That means that I have an odd function times an even function, and that's automatically going to go to 0. You should verify that by plugging in the antiderivative. But in the first component, I have something that's not going to vanish, and so fq is going to be equal to, and it's not the prettiest expression, but it's one that we can evaluate. Kq lambda times L over x. Remember, x is the location of the test charge along the x-axis, times 1 over the square root of x squared plus L over 2, quantity squared. And then, of course, because it's a vector, the z component of that vector is 0. Now, once I've written this down, you can say, well, Tom, if I just look back at the picture, of course the z component of this thing is going to vanish because my charge distribution has a symmetry across the x-axis, and therefore it wouldn't make sense for a test charge along the x-axis to feel any up or down force. It would just feel a force in the x direction. But at the end of the day, I've used a fairly simple method to be able to calculate what the force is on this charge given the multidimensional representation that we have of Coulomb's law.